Let's get some practice exercises that allow us to write some code that throws exceptions. Now, I guess I sort of want to work within somebody else's framework, so I'm again going to ask ChatGPT to generate me some starter code, because basically if it generates me exercises that amount to write a program that has a function which throws an exception, I don't think I'm getting as much out of it. I think part of the difficulty of using exceptions in practice has to do with the fact that often you're required to throw exceptions that somebody else has designed, or at least in cases that somebody else has dictated. So having that extra constraint, I think, is helpful. Now, that said, because this is a conceptual subject like references, it's hard to know what ChatGPT will come up with, so maybe we could play around with its ideas a bit. So I'm practicing exceptions in C++ or C++ 20. Can you generate a programming exercise in the following form? The exercise is a C++ program with at least 3 functions missing and for me to implement. Each function somehow involves throwing or catching exceptions. Now, one thing I have to keep in mind is that it might give me an exercise that involves catching exceptions that get thrown out of the standard library functions, and I might have to go look up the standard library functions to figure out what those exceptions are. Each function, these are separate bullet points. And then I want a header comment. Each function is preceded by a header comment containing a formal specification. Last time I asked for a formal specification, what it gave me wasn't really that formal. The main function is already written and contains multiple test cases for each function. Don't show me the solution. Certainly. Okay. Let's see. So we've got, it looks like it has correctly identified that I was sort of angling towards the standard exceptions. I might want to ask it a second question to get some practice throwing customized exceptions. So function 1 is dividing 2 numbers. That's pretty straightforward. Function 2 is factorial. So I've learned that ChatGPT loves giving factorial exercises. I'm actually surprised it took this long to get to this point. And even better, so when I was doing factorial exercises in CSC 111, it didn't do this. ChatGPT has identified that when you compute factorials, they get large very quickly. So it's actually had the factorial function return a long int, which gives it additional range. Finding the square root of a positive number, okay, well, that's a little bit of a tall order. And then in each case, I throw one of the standard exceptions. All right, so yeah, that all looks good. We've got here, oh, its testing code is actually pretty bad. So the issue with this testing code is it's one massive try-catch block, and in the try-catch block, we just catch generic exceptions. And this is a problem for a few reasons. If you were to write code that did this, this would be considered very bad form, extremely sloppy. Like that is, if somebody gave you an interview task involving writing a bit of code and you wrote this, you'd be done. Like they would say, this person does not know C++. Because, and actually, arguably, in any other language with exceptions, this is also very sloppy. The point of exception handling is to have some, in a sense, sort of dexterity with dealing with exceptions. You want to know what kind of exception was thrown and who threw it. This is just saying if anything gets thrown, catch it, and then the program ends. I won't even be able to use this testing code because this call to divide numbers throws an exception and the try block just ends. So I'll never be able to test these. I'm going to complain about that. I'm going to say, that's all right. Can you modify your testing code to catch exceptions with more granularity? So, for example, I want separate try blocks for each test, and I want catch blocks for specific exceptions, not general ones, not the general std exception. It should be able to understand that request. Okay, so here's a new main. Okay, this looks a little bit more like what I want. Okay, it's going to take a while because it's going to. I've asked it to generate a great deal more code than before. While it does that, I'm going to go up and copy the original template. So that would be this. And then I'm trying to think about what I want to do for exercise for function number 3. Okay, so we've got that. I'll save that. I'm going to go and now grab the new main that ChatGPT wrote, which broadly does look like what I want. It's pretty long, but it does look like what I want. So I'll go back over. I'm going to replace this terrible main that it generated, the sloppy one, with the new one. I'm pressing paste. Is it not working? Or okay, there we go. Okay, so what we have here is now a specific try block for each of my individual tests, a catch block for the specific exception that I expect to show up, as well as this generic catch block, which, I mean, fair enough. So I've mentioned in class and in other videos that this type of catch block, the ... catch block, is not something you should rely too much on. So it is considered very sloppy to use this in any case where you actually expect it to be run. That is, if you're expecting an invalid argument could be thrown, you should not be catching with ... And also, because if you catch with ... you prevent exceptions from flying over your head, which is a bad thing, because if there are exceptions you don't know how to handle, you shouldn't be catching them. So this is not generally a good idea to use this. In the sort of best case, it's harmless, but it doesn't add anything to your code. It might be helpful for debugging, but that's pretty much it. I'm gonna give ChatGPT the benefit of the doubt and say maybe it's adding this because it knows I'm doing a contrived exercise. All right, so there's my divide numbers tests. I'm expecting that the third divide numbers test gets an invalid argument. The factorial test, I think we should get factorials. It says, yeah, throw an invalid argument if n is negative. So factorial of 0 is valid, and it should equal 1. And so I think the third factorial test should throw an invalid argument exception. And then for square roots, the third square root test should throw domain error. Okay, so these are nice because the first couple are pretty easy. So what I'm going to do is divide a by b, but if b is equal to 0, and I'm going to use an actual equals comparison here. So I'm not going to bother with a range. I'm going to say if it's literally equal to 0, then I'm going to throw the exception. So if b is equal to 0, then I'm going to throw invalid argument. And I'll give it a message saying can't divide by 0. Now, otherwise, I'll just return a over b. Okay, there's divide numbers. I'm not going to. I guess I'll try testing this as it is. Okay, so those are to be expected. Practice exceptions 1. Now, of course, all the factorials and square roots are coming out looking incorrect. Yeah, I mean, this is a weird coincidence. But if I look at division, 10 over 2 is 5, 25 over 5 is 5, 100 divided by 0 equals invalid argument exception. And you can see that's where it caught the exception. I'm realizing this wasn't a great set of test cases for a couple of other reasons. One of them is that I want to make sure, not that I'm actually worried about this, but I want to try dividing something that results in a fractional output. So not just 20 over 5. Okay, so it comes out to be 3.8. Okay, that looks good. So it looks like divide numbers works. I don't think I need to test it exhaustively. Now, factorial. So a reminder that if I want to compute the factorial of an integer n, that would be written n exclamation point. That is the product of all of the numbers, the integer values from 1 up to and including the value of n. So 3 factorial is 1 times 2 times 3, or 6. And that's 3 factorial. As a special case, 1 factorial is just 1. 0 factorial is the product of nothing, which I consider to be 1, and most mathematicians would consider that to be 1, an empty product to be 1 as well. Depending on where you learn factorials, you might not think that, but I think that, and I'm going to do that. I'll bet ChatGPT agrees with me. If you want to know, go ahead and ask it on your own. So I'm just going to write a loop that loops from 1 up to n and multiplies everything together, unless n is negative. Now, because I'm taking my argument as an int, it could be negative. Now, that's contrived. ChatGPT could have made it so it takes an unsigned int, but it didn't. If n is less than 0, then I'm going to throw invalid argument. Let's see. can't compute factorials of negative numbers. Now, there are people that have defined extensions of the factorial function or the concept of a factorial to negative numbers. You can go ahead and look that up, and I think if you do, you'll understand why we do not want to deal with that problem. Factorials of negative numbers, okay, and so that's the exception that I throw. Otherwise, I go compute the factorial, okay. I want to use unsigned long, okay. I like to write the type as unsigned long int. It turns out you could just write unsigned long, but it feels sort of like adjectives with no nouns, so I like writing int. I'll call that fact, and we'll start that off at 1, and then I'll just loop from 1 up to 4. I have to make sure I use the same type, because otherwise I might run into truncation issues. Unsigned long int I starts at 1. It counts up to n, and then I++. And I'm going to multiply fact times equals I. And then I return fact. So we'll try running this. Oh, interesting. So it's giving this warning. So this comparison here gives the familiar, you shouldn't be comparing signed and unsigned values warning, which is true. Unsigned long int is unsigned and int is signed. To make the warning go away, I'm just going to turn n into an unsigned long int with a cast. This is a C-style cast. There are those in the C++ community that would argue that I should use a C++ cast. I am not one of those people. I'm going to use a C-style cast for numerical casting. So that's going to make the warning go away, and it's nice if the compiler doesn't complain. Okay. Yeah, good. Okay, so I'm going to run this, and let's see what happens. Factorial of 1 is, factorial of 0 is 1. Factorial of 5 isn't 24. That's a bug, so I've made a mistake. The mistake I've made is that the factorial of 5 is actually 120. I happen to know that because I compute factorials often enough. 24 is the factorial of 4. So I realized that what probably happened was I should have been counting up to and including n. Okay, so now it's 120. I'm going to add another test case. The factorial of 3 is 6. Let's try computing the factorial of 3 here instead of 0. We know it works for 0, so we can remove that test case. All right, factorial 3 equals 6. I'm going to declare the factorial function to be complete. It is throwing invalid argument on my negative argument, and even if there were a bug in the arithmetic, frankly, I mean, you know, the exercise is about exceptions. Okay, square root. Now, I was not expecting it to throw this at me. So I'm going to first handle the exception case. So all it says is if x is negative, we can't compute the square root. We actually can, but it's a complex number. And because this function is supposed to return a real number, so double, we're in trouble. C++ does have a complex number type that we could use, but we're not going to do that. So if x is less than 0, we throw our exception. Oh, there we go. So I will throw std domain error, and then I'll just say can't compute square roots of negative numbers. Now, what do I do otherwise? Okay, so the cop-out would be for me to just call the standard library square root function. I guess to demonstrate that, I'll try out that cop-out, std square root of x. Now to do this, I have to bring in the math library, which is called cmath, because it's actually, this is math.h from C. So you might remember square root from last year in 111 in math.h. If you want to use a C library feature, you take out the .h and put C in front of it. So I'm using cmath. There's my cop-out. And I feel like this is, so on an exam, if you know a magic library function that solves the problem and you know how to use it correctly, you will get the marks for using it unless the question specifically says you don't. So if it says don't use the library or don't use the square root function, then you can't do it. You'll get a 0 if you do it and the directions say not to. If the directions don't say that, you're allowed to do it and you'll get full marks, even if it feels sort of like cheating. As long as you do it correctly. If I use the function incorrectly, then then there will be trouble. We'll try running this and I'll show that it works. Now, it does sort of feel like this is phoning it in. I don't know. Can I generate a solution to the square root algorithm off the top of my head? This is a good challenge. Here's the way I'm going to do it. I'm going to use a method called, there are two ways I can think of that will work for computing square roots. Remember that the square root that we compute will be approximate because obviously I only have a certain number of places of decimal precision. The two methods I can think of are bisection and Newton's method. Most of you have probably seen Newton's method already in a calculus course. I know Newton's method, but I don't know that I could produce code for it as quickly as I could do for bisection. So the idea behind bisection is that the function, it's easy to know whether something is the square root of x. So for example, if I've got this value y, and I want to know whether y equals the square root of x, well, all I have to do is to square the value of y and see if it equals x. The other thing that's interesting about the function y squared is that if I just sketch it here, I'll sketch out the positive part only, it's continuous. I know that there's a value that's definitely too small to be the square root of x. That's 0. I also know that there's a value that's too large to be the square root of x. That would be x itself. X itself will always be greater than or equal to the square root of x. So what I could do is I could say, hey, let's start with the interval 0 through x, and then just narrow that interval down until I get to the square root. So for example, suppose that I have the interval 0 through x. I look at the value halfway between, so that's x over 2, and I square it. If this value is greater than x, then it looks like x over 2 is bigger than the square root of x. So I'm going to narrow my interval down to be 0 to x over 2. On the other hand, if this value is less than x, that means x over 2 is smaller than the square root of x, so I'll narrow my interval down to be x over 2 through x. And then I'll narrow my interval again. I'll look at that interval and choose x. This would be 3x over 4. I'll choose the value halfway between the low end point and the high end point. And then I'll narrow my interval down again. So maybe I narrow it down to be 3x over 4, x over 2 to 3x over 4. And I just keep narrowing it down until these two numbers are close enough together that I basically have the square root. That's called bisection because I keep cutting the interval in half. Let's just see if I can implement that convincingly in this video without looking it up. I've had to do it enough in my life that I probably can figure it out. So I'm going to do double lower, and the easiest lower bound to start with is just 0. Double upper, and we'll start that off at the value of x itself. Because x is not negative, we know that the square root of x lies between 0 and x. Okay, so now what I can do is I'm going to write a loop. So I have to figure out how close together do they need to get before I'm satisfied. Now I'm going to make this up. You could easily change this. I'm just going to say while upper minus lower is greater than, well, like I'm going to do a number like this, but I'm going to write it in scientific notation. So 1 times 10 to the negative, let's do negative. Double typically has about 16 digits of precision. Let's do 14. So this would be a 0 point and then 14 zeros and then a 1. So 10 to the negative 14. Okay, so I'm going to keep going as long as upper minus lower, the gap between them is this much. And then when I return, I'm eventually going to return the average. So upper plus lower all over 2. All right, 2.0. Just for appearances. Okay, so in each step I compute the midpoint. So midpoint equals upper, that's also going to be just the average of the two values. So upper plus lower divided by 2.0. And then I ask the question, if the midpoint is greater than, if midpoint squared is greater than x, well, that means that mid is greater than square root of x. And so in that case, my new upper bound is my midpoint. Now, otherwise, then the lower bound becomes the midpoint because that's implying that mid is less than the square root of x. I'm not even going to care about the equal case because this is going to, if all goes well, this is going to converge eventually anyway. This is the same as what you might do if you had to guess the square root of something. So if I said, give me the square root of 7 to 5 decimal places, and I give you a calculator, and the calculator doesn't have a square root button. All it has is a square. You can do multiplication. You could just guess. You could say, well, let's try 3, and then 3 is too big. So you could try, let's try 2. So the idea is, you could just approximate it iteratively by narrowing your range down and slowly, improving your estimate. That's basically what I'm doing here. It's called the method of bisection. It's not the point of the video, which is why I didn't just give you a lecture about bisection. I just want to show that I can implement, that I can live up to ChatGPT's expectations. Okay, so we'll see if that worked. And okay, I mean, it's giving 4 and 5, but that's not that exciting. Let's see what happens if I give it some fractional value. So let's do the square root of 7. Okay, square root of 7. And then I'm looking around the room I'm in to see if I have a calculator. Let's do the square root of 100. No, that's going to be 10. Let's do the square root of 10. Okay, so apparently, I'm going to pull up a calculator on my other computer. Okay, so the square root of 10, or the square root of 7, is apparently 2.64575131. Yeah, so that looks correct. What's the square root of 10? 3.162277, and that looks good. It looks like the print statement rounded this up to an 8, but I suspect that all the precision was there, but the print statement only wants to give me 6 significant digits. So, okay, I guess I somehow was able to write a function. I'm sort of pleased. I'm sort of proud of myself for that. I was able to write a function that produced a square root. This is a neat exercise. Doing mathematical exercises like this in programming actually is really interesting. Like, it's a really useful way of practicing programming because you have to apply 2 different sets of skills. You have to figure out how to compute it and then write the code and believe the code, which that's what I was doing in this. Behind the scenes, my hesitations while writing this wasn't, oh, can I write a loop? It was, now that I've written this loop, do I actually believe that this does what I think it does? And I guess it did, so I'm sort of happy about that. And then finally, the test case we care about, when I try and compute the square root of a negative number, we can see that it says can't compute square roots of negative numbers. Okay, so I guess there are exercises for practicing writing code that throws our standard exceptions.